Hi all, this is Claudio from expertfea.com with the new live stream containing simulations in the biomechanics field. Let me share my screen firstly. And I'm going to simulate something like this. So we have a plate, some screws, and also would include something like this. Spinal element called interbody cage or fusion cage. This one, okay? So let's see what we have here. Here, this looks nice. All right, so I investigated a while and I have found this article. Firstly, let me give you a reminder about my website, expertfea.com. Hundreds of simulations, tutorials also in biomechanics, videos, books. And remember, if you are stuck with your simulation or you just want help on your project, on your thesis or diploma, mail us and we can help you. Where was I? I said that there is this article from the Nature paper, which we know I think it's #1 in the scientific literature. And my purpose is to kind of imitate or get inspiration from this paper. So I would like to do something like we see here. We have a plate, screws, and a fusion cage, and this is the middle case. Let's say I will not waste time with the before, with the healthy spine, let's say, and I didn't find this 3D model, so I'll not deal with this, only the middle case. So let me show you, at least let's take a look here. Also, we have the boundary conditions here, yes? This is fixed. Here is a portion, it's almost the entire cervical part of the spine. We know we have 7 vertebrae, include the atlas and axis or whatever it's called. Do I have a name here? No. And we're going to apply compression force and the moment. And we will investigate the stress in the mechanical parts, also in the bone and in the cartilages or the discs, let's say, contact pressure and whatever we can extract from this FEA. So let me show you what I got at this moment. I got the spinal implant. I have also the plate with the screws and, of course, the spine. All of these are found on grabcard.com. Or I will have to warn you that there is some work to be made. Here there was some work because this was made up to, there were some tightness errors. So this file was IGS with lots of surfaces, and I kind of filled it to become model, or I solidified it, let's say. And this didn't necessitate any work. Only what I don't like that is the fact that it's a solid body, let's say. I would have liked to have an assembly, for example, at least 2 parts. This screw and this. All right. So also, as a short reminder, please take a look also on my live stream 12, because I have done something similar. Now I will move to the next stage. I'll complicate it, let's say, yes? We have fewer vertebrae here, only 3, and yes, this is a, let's say, a simpler case, made in explicit dynamics. My intention now is to start with static structural. Why? Because I would like to see the contact details. I'm talking about contact pressure, which cannot be found out in explicit dynamics, only in static and transient structure. So this will be my this is my intention to work with static structure. If it's not possible, if there will be problems, I foresee lots of problems. I'm talking about the contacts between the screws and the vertebrae. And here some contacts, there will be some problematic contacts here because we will have in the geometry you see here, there are some teeth, let's say, which will cut from the vertebrae, and this will impose problems with the contacts, problems which are harder to solve in static and transient, but they are pretty easy to solve in explicit dynamics, let's say. So without further ado, let's get to the order of business for today. Firstly, do we have any question from the large audience of 0 people? No, there is no question at this moment. All right, so let's count them. This is the cervical side. 1, 2, 3, 4, 5, 6, 7. In the paper, it holds also the first thoracic vertebrae. 1, 2, 3, 4, 5, 6, or maybe not. Yes, because they removed the top vertebrae. They began with the third vertebrae. You see it here. So they began with the third cervical, and they ended with the first thoracic vertebrae. Yes. So let's do the same. We will delete C1 and C2 and keep T1. This is T1. So let's delete the first two. 1, 2. We don't need the cartilage, of course. And everything that is below here with Control pressed. Yes. Let's do something like this. Right click, locating structure tree. So we have some. I don't need this cartilage. Am I right? Yes, I don't need cartilage. What we see here, they have the spongious side of the bone, which we will not use. We will not deal with today. According to my assumption, I think they kind of cut this portion. You can see like a green, teal, gray, whatever color, and here is pure gray. And I think they kind of split the spine in 2 parts, one on the left and one on the right, because here on this part, what they did is they kind of constructed the spongious, the inner side of the bone, which usually has a lower density than the cortical, the outer side of the vertebrae. Yes, they kept, for example, here. Yes, here there is no spongious and cortical, but here it is spongious on the inside and cortical on the outside. This is why they split, and they dealt only with these. Pretty interesting. They also divided the discs into inner and outer. You can see here, inner kind of gray and outer, inner kind of green. and outer kind of gray, because they also have different densities. And let me remind you what I was talking about. Spine disc, spine disc regions, spinal disc region. Okay. This is what they tried to simulate. No, not this. This one, yeah? So look here, there are many areas, but definitely there is an inner side and an outer side, okay, with clearly different densities. I'm talking about this side. Let's see if I can zoom in, just for fun. Can I zoom in? Yes, I can. Look here, what I was talking about, yes? Because they have different densities, they treat them with different densities. All right, enough about their model, which of course it looks nice. And by the way, it was published in Nature. In this live stream, you can imagine we're not going to publish the FEA in Nature anytime soon. So we'll not use the different densities here because I would like to focus on the modeling and making the FEA work, which is pretty complex or cumbersome as it is, but also spending time with different densities, cutouts, and separating the cortical and the spongios, it's a lot of work. And as always, I would like to present FEA results during the live stream. Yes, you can imagine this FEA took maybe a few days, the modeling and multiple iterations in order to obtain decent results, publishable results. Yes, so it's a lot of work. Okay, so we can see, for example, that the height is 102, 10 centimeters, yes, 100 millimeters, because I'd like also to measure this height in my space claim. Firstly, we do have some artifacts from a different part, which we do not care about, because some parts were deleted. What we're doing now is right-click, delete empty components. So we stay with what we have. Why is this coccyx here? I don't see it. I don't care about it. Let's see if we have only these parts. Yes, I don't want extra parts. Let's heal this because you can see that it is a surface body. What I do not like is, what is this? T12? What? T1. This thoracic vertebrae is kind of split in multiple surfaces. Hence, what I will do is hide others, right-click, invert visibility. So I'm keeping these three surfaces. You can see this is split and there is another split surface, this one. These two are kind of split, all right? Let's unite them. This is a surface body. We want to obtain a solid body, meshable and accessory mesh. So we have the repair tab. Usually I'm going for missing faces, usually. Let's see if it works with this. You know what? These faces exist. Yeah, there are these extra faces. So I will not heal as it is. Instead, because these faces exist separate, I will go for something called maybe stitch. There are no stitch, all right. Maybe gaps, no. So it's done. Let's hide this face and this face, and let's see. They are found as missing faces. Let's see if a space claim can replace them, can patch these missing faces. Oh, yes, it could. Perfect. This is 3D. Now, of course, we don't need these small surface patches. Let's delete them. Right click, show up. Now we have everything we need regarding the anatomical side. Yes, because we are going to move to the implant side. Let's say. So at this moment, let's right-click source internalize all, because we do not want to have a dependency with a previous 3D model, with the previous file, the originating file. And let's give it another name. Stream 28, superb spine plus screws. And we have also, we will insert the cage, fusion cage. It's kind of a mouthful, but let's quit the superb or whatever, because whatever we do is superb after all. So I saved this. Now let's begin bringing what we have. So we have this assembly. Let's select all of them with Shift or Control pressed. Right click, move to new component. Yes. Why I'm doing this? Because I'd like this top, let's say, subassembly, to go for design tab, and we have a copy here. Copy. And here we are going where we have the spine, and Control V or paste. I could have pressed paste here. So they are kind of thrown away in the macrocosmos. So what we do at this moment, we're going to move one subassembly towards the other. All right. Zoom extends. Perfect. So it's kind of what we need and what we want. Just for fun, let's rotate it with maybe 90 degrees. Let's look from all the positions. It's kind of useful and interesting. Where was this 1, 2, 3, 1, 2, 3, exactly in the middle. All right, let's do kind of the same. This is the so-called middle. Only what they have done is something like this. Remember the move command, yes? What they have done is, I don't know if they have a screw. No, they don't have a screw. Look here. So there is no screw to edit the tightening or the position of this fusion cage. There are certain plates, for example, my plate. This is my plate, which I think with this plate, I think I can modify. Yeah, if there is a screw here, if there were a screw, we can modify the configuration of the fusion cage. But now I see that it's a little lateral, so maybe it's not the design. Yeah, maybe my plate is not the best plate for this scenario, maybe. So what I would do is I can scale, because we can see it's too much. The screws are too. Let's obtain a read. For example, the diameter of the screw is 10, but let's ask for an average diameter of the screw. Average diameter of pedicle screw. Pedicle, sorry. So it's 5 to 7, and we have double. So let's scale it 0.5. This sub-assembly, yes, because it's too much. So what we can do is, firstly, let's save, and I'm going to hide the spine. Do I hide the spine or not? I'd like to keep it in order to have it as a reference. So let's go here with pool. Scale body. We choose a point. We don't care exactly what point. And now it says select one or more bodies to scale. Let's drag from the right to the left, but it's selecting only surfaces. I would like to select bodies. So pick an anchor point. How do I select? No, it's not possible. Let's see. I lost it. So I triple clicked to select a solid body, yes? So let's triple click the other parts, but with control pressed. No, let's, we don't need a triple click, we need just control pressed. They kind of know that we have solid bodies. The software knows, so it's pretty easy. I said something like 0.5, 0.7, but I can also drag with the mouse. What value is this? 0.67, or I didn't see it. We don't care too much, because in reality I would like for the screws to, yeah, so I need to scale it again. Control Z, Control Z. Let's assign another 0. Maybe 85, a little less. All right. Now let's go on Move. Select the sub-assembly, and let's move it. I think we can do even better. Or do we leave it like this? Let's scale another 0.9. So instead of the 0.85 that I said, let's make it 0.65. I think it's an overkill, so let's go again with 1.1. Here move, and my goal is to have the screws in the middle of the vertebrae. And here it's not so much. So Control Z or undo. Let's hit it with 1.25. Because the previous 1.1 was not enough, now I have modified to 1.25. Let's move, and we should be nice finally. Yes, we're very good. So, you know what? This is what we had at disposal. I mean, we're not going to need this screw. Yes, we're going to use only this plate. And in the meantime, we're also coming with this spinal implant, whatever. So, copy and paste. Of course, as always, it is thrown in the universe. Let's call it cage. Maybe I should have named it Nicholas. And let's move it here. I think I'm not the only person who named this part Nicholas. Maybe I know. I'm not the only one, maybe. So let's save, of course. Can I close the other parts? Let's close them. All right, so of course this is kind of too much. Let's triple click and rotate it with 90 degrees, yes, and let's scale it. Pull, scale body, this body, how much? I forgot to click the anchor point. Then the body. All right. Let's do it kind of visually, something like this. 0.25, for example. Yeah, and let's see if it's enough. Move. Yes. And inside. I think it's kind of too much. All right. This part should be 1, 2, 3 here. Here, I mean in between. And it's yeah, it's too big. Okay. So let's scale it again with 0.85 maybe, yes? Or 70, 0.70. Pull, anchor point. It remembered? 0.7. Yes. Maybe more is needed. Let's hide this plate at this moment. And these parts, let's make them transparent. click a face, transparent, click a face, transparent. Of course, I don't need the disk. Triple click, delete, triple click, move. I am kind of exactly, I'm talking on a microscopical level, exactly on the axis, but we do need to reorient it to kind of replace the former disk, which was excised or surgically removed. We can scale this down another maybe 0.85. Pool. I'm sorry for not having the proper dimensions. Yes, these are parts taken from grabcap.com. I didn't model them. I don't know who made them. All my thanks to the original authors, but you understand, I need to adapt because these are not up to specs or the dimensions, you know. They were very big, so they were not realistic. Scale this again. We are going to choose a point kind of in the in a middle, if we can talk about a middle. I would like this cage to keep its references, let's say, and I'm selecting the 3D model. I said 0.9. Is it enough? I think it's not enough. No, it's not enough. It should be even smaller. Pull, drag 0.9 again, and we're going to move it here and here. Yeah, I will remake the vertebrae opaque because they are transparent and it's hard to understand what I'm doing here. Not only for you, also for me, it's hard to understand what I'm doing. This screw, this kind of impedes me here. The vertebrae collides with the screw. And sincerely, at this moment, I didn't plan to modify it. So for the purpose of this live stream, I will make my life easier, hide others, and I will cut the screw because sincerely, I don't intend to modify the configuration of this part. So we don't care too much. Split body, click a target object, then the face. I will split this body and remove. Very simple. Just for fun, is there a way to remove also this? Why I'm talking about? Because if I leave this, then it will not be flexible. This should be like a spring. Yes? Because there will be a top compression, let's say, or from the bottom. If I have this big protrusion here, it will limit the spring effect because I would like this gap to close. Now it's like this, and because I have this in the middle, I am limited. So if I remove this bolt, then I can have the spring effect, yes? So let's click these faces and hopefully get rid of this element, hopefully. Unfortunately, I forgot one face. Delete. Yes, very smart. Do I need this? I don't need this. Select protrusion. Delete. Now we have the proper spring, yes? Show. Yes. It's still too much. Let's scale it again with 0.9 if possible. We pick an anchor point from here, 0.9. Another 0.9, and that's it. All right. So let's make the cage kind of horizontal and rotate. All right, maybe it's time to convert these parts to being opaque, because I would like to create a section view. Ooh, this looks so nice. So I promised a section view. I will click a face, then create a plane on that face, and I'm going to rotate this plane. Move, double click here, and it will perfectly rotate to 90 degrees, which will coincide with the middle, with the solid axis of the vertebrae, or axis mundi for the philosophers. Click the plane, section mode. Look here, yeah, so we do need to kind of rotate this even better. This cage, let's do something like this. Ooh, this looks nice. I'm thinking in the meantime if I want to scale this. Yeah, I think I will scale it. Let's save and 1.15. So pick an anchor point somewhere in the middle. We'll call this middle. This is the cage, and I said 1.15. Yes. Back to the section view. Click the plane, section mode, and let's reorient the cage. Click the cage. We have the move here, the move command. Oh yes, it looks so nice. This is a little too much for me. What I mean is I would like to cut this one. Let's see if I can cut. I will, if I, let's keep only these two parts with Ctrl pressed, hide others. So if I cut here, we will have other parts remaining. Let's do it, because I would like you to see the command. Let's save before doing something destructive. Split body. It says a target object. This is the target, and it asks for a plane, face or plane, whatever. I will ask for this face. So this is the part that I would like to remove. The problem is now it cut only also these ones. So let me re-merge them. Let me rejoin them together. Combine, click this part, and I can click here with plus. This will be joined to the original part. This, this, and this. But I have now complete visibility here, escape. And yeah, it looks more professional, let's say. We can also kind of cut here, but I don't want them overkill. Let's leave it like this, all right? Because we do have something nice, let's create right-click source internalize all. Let's create another version. Once in a while, we need to create another version. All right. The screws are still chunky. The radius is so much. Because we have only 4 screws, I was wondering if I can scale them. Let me also move a section view between to see the screws and the plate. Yes, so I'm clicking the plane, click the move button, but because I would like to copy it, not move it, I'll press Control, and drag. I will drag this to pass through the screw, and now it's passing almost through the middle of the screw. Yes. Now to have a section view here, we click this plane, section. So I can see now that the screws are definitely too big, yes. Also the section is not exactly through the axis of the screw. Now I also see that the discs need scaled down. We need to make them smaller because the collision is too much. This is a good scale here. Also kind of good and also kind of good. Only here, this is too much. We will solve this a little later. Let's see if we have any question from our audience. Yes, there is a question. Hi, sir. Hi, Aravind. I have an additional question. Regarding the appropriate chassis for navigating, do you happen to have any comparable solution? Comparable solution. So I gave you on the last stream, I gave you 2 or 3 scenarios. Compare between them. Sincerely, I don't have what to compare. I will also show you these. I have 2 simulations with wheels, and I'm talking about these ones. These ones. Remember about these ones. This and this. So this is my first. Remember, motion simulation of a field tire pressing on a rotating drum. and also this one. But this is an airless. Yes, it's not filled. Yes, airless. It's kind of wrong to say airless because air goes through. Yeah, other compare. I would like to show you this thing, which is this deals very well with the contacts, with the wheel contacts. I'm talking about this one and also this one. This one. This is it's exactly on what you need. Only if you are going to purchase this simulation and see the boundary condition. This is exactly what you need. Something similar here, but it's wheels on tracks, let's say. Yeah, it was a lot of work here. All simulations are a lot of work if we want to make them decent, not using default bonded contacts. So I gave you the reply. Where was I? Let me delete all the screws because I would like to kind of pattern them, yes? All the screws, all the screws that I don't need. So what did I say? Let's go for anchor point. And let's choose the screw. This is the screw. 0.9? Yes, 0.9. Now we're going to look through the section view of the section view. Now I see that it's not so nice. It's not aligned, let's say, with the screw, but let's click session mode. Now the screw is much better. So let me go here and kind of move it. Also it outwards a little because there is some contact, microscopical contact, but we always want to avoid collisions. So let's go here and let's ask. I selected with control pressed, right click, hide others, and I will ask the software for collisions. Prepare interference. So there is an interference. All right. What we are doing is design move. I remember the collision was on that side. I can move it, but I can also rotate the screw. What should I do? I can translate it, but I can also rotate it because it's clear to me that the screw is not properly aligned. What is this? So the screw is not properly aligned with the hole. Why do I need this small sliver of surface? I don't need it. All right. Yeah, I have seen better screws. This is what happens when you take free stuff. I said let's rotate it, but let's rotate it from kind of from the middle, you know. 1 degree. Oh, 0.5. Oh, yes, it's kind of 0.4. All right, so let's go to prepare interference. There are no interfering bodies. So I was inspired. What we are going to do is select the screw and move with control pressed. With control pressed. Let's move it into the hole as centered as possible. So, for example, prepare interference. There is a small collision here. So instead of 22.78, I will make it 22.75. Let's see. Prepare interference. Perfect. No interfering bodies. All right. Let's kind of copy them and mount them on the upper holes. So this is the other screw. With control pressed, click on the move command. With control pressed, we are going to obtain a copy of both screws. $75.45 or 75.42. It's just guesstimation, all right? They are not properly aligned. Nevertheless, let's hit a save here, and let's show a plane, this plane, and let's look on the. Here, I'm interested about these two screws. Click the plane, click the section mode. So there are collisions. The holes are not very well made. Either we rotate. Oh, we definitely need to rotate. 1, 2, 3. Move, and we're going to rotate them in a guesstimating manner. But I would like to move the mass, the coordinate system, maybe around here. It will be in the middle. Yeah, because I would like to pivot around these the head of the screws. So let's do what I was talking about. All right, and let's move them. Oh, it's too good now. We can go again in section mode. Click the plane, click section mode, and pull them. Yes, I can pull this and this with move. There is a move. I don't know why it's referenced here. I don't care. I'm looking here, so pay attention here. Now I see that here they will collide firstly here. So let's bury them in the hole. I didn't select the correct screws. These are the new screws. Let's bury them in the holes, something like this, and maybe move them a little up. I think I'm talking like Bob Ross when explaining these. You know, there are no accidents, only happy. No, there are no accidents, only happy mistakes. Yes. The Bob Ross of FEA. Yes. Look where was I? The Bob Ross of answers. All right. Let's kind of accept what we have. And let's check again. Let's move these two screws to this subassembly. And let's check for interference. Prepare interference. Yeah, they are buried a little too much. The easiest solution is to pull them out. Let's do what I said. With control pressed, design, move, and let's pull it. How much? No idea. 0.5. All right, 0.5 and prepare interference. No interfering bodies. How cool is this? So we solved this subassembly. I need to keep it as a subassembly because I will move it further on. So right click, delete empty components. This is T1, not T1-3, and these are the disks. T0, there is no T0. All right. Now, let's proceed to the final part of the model. And let's perform the surgery. This is the surgery that I propose. Only the screws, oh my god, they are going to too much. Degrees maybe, and let's move it a little upwards. A few more degrees, 2 degrees, is it enough? It's kind of enough. Why am I here when this subassembly should be here? Am I right? Yes. You can imagine in an operating room there are multiple people, exactly to remind the surgeon, the main person, to remind it exactly these things. Hey, you have forgot one screw, one scalpel, one something like this. I do think we have extras. It's too much. The screw is too much. There. Let me see in section mode. So I will look for some X-rays. Spine something. There are some X-rays. The pedicle screws come from the outside, from the posterior side of the spine. It's not what we need. Now I see they are using smaller screws. They didn't make a section view to see the screws. They definitely have small screws. So what we are doing is we're shortening the screws. Yeah? So we keep them and we just shorten them. How many? 1, 2, 3, 4, 5. Let's keep only 5. I don't know how to say threads. No, because there is only one thread. 5 peaks. Then cut. Hide others. Do we have a section plane? We have this section plane, and with control pressed, I'm going to rotate it 90 degrees, and I'm going to cut a bundle cut. I don't want precision. Let's select this plane and move it. 1, 2, 3, 4, 5. Something like this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We're kind of there. Is it perfect? It's not perfect, but it works. This is the principle. This is the main idea. So let's split the bodies. Click a target. This is a target. With control pressed, we have more targets. With control pressed. Done. We release control. Click a face plane, whatever. We don't need this. I can delete this plane. And let's look in the section view. I'm clicking this plane which goes through the screws. Section mode. Yes, we're very nice. A little outside, a little inside, it's perfect. All right, now we need to do the Boolean operation, the combine operations in Space Cleaner. Oh my God, the modeling takes so much. If you don't have the time, the patience to wait, go towards the end of the end of the live stream, where you will see FEA results. It took the FEA took the modeling takes so much time that I think I'm going to do it in Explicit Dynamics directly, because there we have easier body interactions. We're going to skip the evaluation of the contacts. It's so much work. So now I get the what? The screws have design problems. Can I solve them? Let's see. There are some cavities which I think maybe they will pose some problems with the meshing. Let's make them transparent. Can I make them transparent? With Control pressed, we have here transparent. Oh no, it's no cavity. It was just the end of the thread, let's say. So everything is nice here. Let's move towards the Boolean operation. Let me copy paste this. No, let me hide it, because it's too big. So I was kind of suggesting to have another disk here. So let's go here in section view. I need a very disk. I don't know which one. This one is the nicest, let's say. Yeah, let's see if I can move it. Just asking for a friend with Control pressed. Oh, it's so nice. Can I or should I rotate it? Something like this. And I think I need to scale it up a little, yes. But I like this. Sincerely, I like this. Let me scale it up a little. It looks pretty weird. It looks too weird for my taste. So what can I do here? Section mode. Okay, let's not complicate our lives. There is a very simple command now. Let's hit save. Source internalize all. Delete empty components. Let's hit save, because I'd like to create a third version. This is the most important version. And because we're going to make Boolean operations to combine the parts, the modifications are, let's say, irreversible. This is why you need to create multiple versions in case we mistake something. What did I do here? Oh, let's undo if possible. I didn't hit press. I didn't hit control maybe. Yeah. Yes, we have everything. All right. For a second, I lost the top disk. The easiest way to solve everything, I'm talking about the combining operation, is this one. Repair interference. The problem with this is that by default is subtracting from the bigger body. Look here. Click an interfering region to subtract it from the larger body. And the question that we need to pose to ourselves is, how do we define, or what is the software understanding to be the larger body out of a pair of, yeah, there are pairs of colliding parts. And the question is, what is the larger body? Do we have a larger body in volume, or do we have a larger body in surface? So if we click here, the complete, it's doing automatically. It's magic, only we can have some logical problems. For example, if it decides to cut the fusion cage, it's not logical, because in surgery we cut the bone. We don't cut the titanium, the metallic implant, of course. This is what I was talking about. For example, I'm curious which one will cut, which one will be cut, all right? Of course, the vertebrae is bigger, is larger than the implant. But will the software understand? Let's see. So let's wait. And let's see if we have any other. Thank you for making these videos. Finally, thank you. Thank you also for the appreciation. They are really helpful. Yes, and they are unique. In such detail, nobody is displaying this in such detail. And I am taking like a risk, I can say. The risk that I'm taking is one thing, and being stubborn to obtain FEA results at each live stream. This is a thing that almost nobody does it. If they are doing it, by the way, if they are doing it, they are doing for already set up assemblies. They are performing FEA on models that they know altogether very well. But you have seen during my live streams that in, I don't know, maybe 75% of the time, I'm using new 3D models. And the new 3D models usually mean new convergence problems. So this is a unique aspect of my live streams. Yes, so I do have the tendency of explaining everything from zero. For me, zero meaning beginning with 3D modeling, and it's not so easy. It's not so easy because it's once you have an unknown, let's say a new geometry, you have unknown and new problems regarding the mesh and the solving afterwards, and the contacts and everything else. So these kind of simulations, especially in biomechanics, they usually take a few days, the setup. Also the modeling, applying the contacts and everything else. Yes, these are my comments. Let's go here on YouTube and ask for ANSYS biomechanics. Oh, I remember there will be this guy, you will see him in 10 seconds. Oh, only my simulations? Oh, nice. And something pretty basic here. Super basic. How medical implants are designed. Come on, and only a femur. Come on. This is pretty basic. Yeah. Ah, this guy. Oh my God. The problem with him is he's using very rough, I would say, immature 3D models. So, AFANET, you have nice 3D models of GrabCAD. Go there, they're free. Use 3D models, even for knee joints. Look here. What is this? It's so awful looking, this knee joint. Come on, you have it on GrabCAD. Come on. What is this? What is this? Ooh. What is? Look here. Why is someone publishing this? What is this? Why are you publishing this? It's sad and laughable. The mesh is so coarse and the scale is so big. It's a scaling problem. Oh my God! No, please, no. He doesn't take in 2 months. No likes in 2 months. He doesn't get the message. What is this? Why do you publish something like this? And nobody's looking. 3 views. And this person is working. No, I will admit this person is working. It's a shame. It's a shame. What is this? It's a scaling problem, of course. Why do you show this? It's so awful. I will not say much. So this is what we need. There are no interfering bodies in the model. Let's escape. And let's dare to save it. Now, the moment of truth. We're going section view. We're going in multiple sections. This is the main section. I talk about the relation between discs and vertebrae. Design section. And with this cage. At this moment, this looks very nice. Very nice. Very nice. Yeah? Very nice. And the other section view. So if you paid attention, is cut. So it's a good Boolean operation. Yes? The software understood. The logic, the geometrical logic, the software does not understand. What am I simulating here about titanium alloy and bone? And of course, it doesn't understand.
And here, let's look. Yes, I'm talking about the screws. Yes. So this is the end of the thread. It's not a cavity in the. What is this? So there are some remnants here, and I don't know how they will impact the FEA. We need to also have a look here, this one. This is a bone rest, let's say. So what I will be doing is, let me hide this assembly, this sub-assembly, and let's look here. Yeah, it's good. It will be very nice, even nicer, when we're creating another plane with control, and when we're going to see this. Section view about this axis on this direction, you'll see that the section is very well made. The Boolean operation is very well made. Look here. So there is no intersection, there is no remaining bone fragments in the screws. So it looks very nice. Come on, it looks very nice. We have to admit it. Also, comparing to what we have seen 2 minutes ago from, oh my God. And this is geometry available for free on GrabCAD. So, ladies and gentlemen, I dare to say that we approach the end of the modeling. I'm curious if they made these cartilages here, because there are some cartilages here. Let's see if they made it in this paper from Nature. No. Between, yeah, here, no, they didn't make. What? I do see some brown areas. Let me stop an alarm, please. 1 second. All right, I stopped it. Oh, yes, they have these cartilages. Look here, what I was talking about. These brown spots here. These ones, I'm talking about this one and this one. And my question will be if I have time to make them. Let's see how hard will it be to make this. How is the moment applied? There is a moment, 1 Newton meter moment, this one. Let's judge it. So it's nice because the moment is not applied in order to compress those parts. The moment is applied in order to compress the discs, and also the force aims to compress these discs. So in this loading, this portion is kind of ignored. Also, I dare say that they separated the bodies. So maybe the gray ones and the small cartilages, maybe they are not part of the FEA. Maybe they are not included.
just a supposition. Let's see if we have results. So it's cut. Do you see? Here exactly what I said, it's cut. Yeah? Clearly we can see that there was a plane which cut these portions. Not this portion, because the vertebrae, let's say, and these discs are kind of intact, but these parts are cut. There is they are called, all right. So they are called processes, transverse processes, these ones. Yeah, processes. Articular process, upper and lower. So these are called processes. So these processes are cut. They are cut from the 3D model, and I dare say they are also not included in the FEA. They exist here just for show, but they are not included in the FEA. I do not see these processes, they are cut. So, which leads me to the conclusion that I will kind of ignore. I will not cut, of course, but I will not also make these small cartilages. No, I will not be making them. Let's save again and move towards the simulation. I will duplicate what I had in livestream 12 because I have kind of the proper materials. Kind of, they can be improved. And this is what I'll be using. So yeah, let's do it. I would like to copy paste. Should I copy paste? No. I kind of wanted to move my 3D model into my work directory, but not at this time. Any question? Yes, there is a question. Or, okay, George. Yes, the cervical disc replacement implant video. I'm trying to follow that through to learn enough to do my own projects. Not many videos in this field, so thank you. Yeah, thank you very much for the appreciation. It means a lot, you know. It's nobody rejected some appreciation, so thank you very much. Also, let's remember that it's free, you know, and yeah, at least let me get some some likes, some appreciation, some nice words. Thank you again. How was this called? Let's right click. But I would like to make this string 28. So let me delete one of the previous simulations. And let's go here, import this thing, because it's open now. And I kind of wanted to have that naming. This is the naming. I want to put it here, the name. And I also would like to change the name. Stream 28, yes. Save. Should I save? Yes, this is my work directory. Just to be 200% sure, let me also upload the 3D model in my work directory. It's here, yes, or not. So double click. Let's move towards the FEA. I would like to rename this to stream 28, but I need to wait for the geometry to be uploaded. This is the older geometry with this shift inside, which will disappear in 1 minute or so. So performing and working in biomechanics simulations is, I would say, is the top of simulations. I mean that you need to know very well FEA to master, let's say, the engineering side. Then you need to know very well modeling, either to start your models from scratch or to edit them. And of course, you need to kind of understand the physiology and the processes that occur in the choreography, in the behavior of the live tissues and live sub-assemblies, let's say. So it's a peak. Working in biomechanics simulation, it's a peak, and it gathers engineering, drawing, CAD, also working in Maya, Blender, 3D Studio Max is beneficial if someone has experience. And yes. And of course, we also need to be armed with lots of patience. So we were here, 1, 2, 3, 4, 5, 6. How many do we have? 1, 2, 3, 4, 5, 6. All right. The main question is, at this moment, will it mesh? This is the main question. The possibility of meshing, yeah, this can be make or break situation. This is why you need to pay attention when abusing of editing and 3D modeling with such complex parts. I'm talking about such complex surfaces. We need to not to abuse too much. If we abuse too much with the modeling and we keep and have and ignore some errors, some topological problems, then the mesh, this solid, the geometry will not be meshable. So let's hope for the best. We don't care about materials at this moment. What we do care is we do care about if it is meshable or not, the entire assembly. So let me prove to you that we don't have a contact tool. We cannot find out the pressure and stress, whatever, in the contacts. This is a disadvantage of Explicit Dynamics. The first thing that I would like here, just for fun, I would like to delete the contacts. And I would like to keep the default frictionless contact between all bodies. And assign separate interactions. You will see in a few minutes. So first things first. Let's change the units to millimeters, and let's assign something like, I don't know, maybe 5 millimeters, maybe. Look here, 4.5. Let's make it 5. And at this moment, I will not assign any sizing. Let's save. Sincerely, I'm contemplating using the virtual topology, which will kind of heal some problems, but only if we have meshing problems. This is the make or break moment. Nevertheless, if there are problems, we will solve them, but it will extend the. So it's look here. We're blessed. We're very blessed. Just for fun, how many nodes? 37,000 nodes. It looks so nice. So nice. Let's make some section views. We do have something in the middle, which looks like this. And I would like also to have an additional section between the screws, just to contemplate a little screws. Oh my God, they look so nice. They look so nice. I will keep the mesh as default, as it is now, because I don't want to extend the solving time too much. So don't expect a mesh optimization. Feel free to refine the mesh. I don't care about mesh quality at this moment. When you're working in your laboratory, team, research, location, whatever, feel free to improve your meshing and the mesh quality. So I don't think virtual topology will improve many things. I'm satisfied with what I have. Can I delete virtual topology? Yes. All right. It's froze. Yeah, no problem. Let's close this and reopen it. Do we have any message? Yes, the cervical disc. All right. Let's open it again. All right. So these are discs. Rename all. Disc. These are vertebrae. let's keep them. This is the plate. These are screws. And this is the cage. Now, let's go with materials. Discs are made with cartilage. I will show the material properties in a few seconds, but they are also available on live stream 12. The bone vertebrae are made of nonlinear bone. The plate and the screws, then the cage, everything, let's make them of titanium alloy nonlinear. This is default, I will not insist on it. Only regarding the materials, these are some properties. Feel free to pause and see them. Did I change? Let's change the unit to have megapascals, yes. So 10 megapascals, yes. These ones are default, a remnant from steel. That's, you know what, let's delete them. Cartilage, isotrope elasticity. How do they appear there? Because they are not here. There is no fatigue defined. All right, the nonlinear bone is this one. I have kind of estimated some tangent modulus. I have estimated like this. So how and why do we have this? They do not exist in engineering data. Why? Why do they exist? We sincerely do not care. All right. So let's go with the. There is a small problem here, so something to be taken into account. If the moment, if the compression force plus the moment are too high, then there will be a touching here. My first thought was to make all bodies bonded. Yes, but it will remove this possibility of having a touching, very nice touching, especially maybe in the middle, where we have maybe a touching, maybe, I don't know. So let's keep them as they are. Then define contact pairs. So for example, everything from now on will be bonded, in my opinion. So bodies, this one with this one will be bonded. What I would like also to have, because there are some gaps in the touching between the parts, there are some gaps. What I would like to do is to make like a pinball radius here. So let's make this 0.51. Let's see if there are some. I would like to see this a small dimension. For example, here 0.25. Let's make it 0.5. Yes, or something in between, 0.35. So bonded. The next bonded pair is, let's duplicate, and I will select this and this. Let's deal now only with the spine and later with the screws, or let's add also the screws. We don't need pairs here. We don't need to think too much about the two sides, the so-called contact and target. No, we don't need to do this. So let's duplicate and here and this one. Let's duplicate this one and this one. Let's duplicate this one and this one. And the same, this one and this one, and the screws. All right, duplicate again, this one and the disc. Duplicate again, disc and vertebrae. 1 second. All right, I want to be 100% sure. Duplicate. And the last duplication. So now what is left for us is to deal here. The question is, will I leave this frictionless? Or I will say, you know what, I will say that all these are bonded here because they are very tightly screwed. Yes, so it's screwed so tight that these are bonded. This is what I will pretend, okay? Perfect. So I said bonded and 0.35, why not? Maybe I need to decrease a little this value. Should I decrease it or not? Aren't they bonded? Oh, what is this? So, yes, in here, let's rename it to 12. For the sake of conformity. Yes. Everything is kind of nice. What I wanted to say is, let me modify this to 0.2, maybe. We do have connections, I have mesh. In that paper, the bottom faces were fixed. Let's do as the paper says. Is exactly as in the paper? Yeah. Did we use the same 3D model? For the spine. Yes, I can bet. Yeah, it's exactly the same 3D model for the spine. All right. We have different implants after all. And let's go here and assign the moment. Let's see if the application of the moment is as identical as they have. No, I cannot insert a moment. Oh my God, I cannot insert a moment. In Explicit Dynamics, you cannot insert a moment. I can, however, I think I can imitate a moment, maybe. So the force is, how much is the force? 33.6. Let's make it 73.6. Let's make it 74. Click to define what? The direction is almost. It's almost on the Z direction. Minus 74. How do I create a moment? I do have a remote displacement and I have a rotation here, but this is a displacement, it's not a moment. Let's ask ChatGPT, all right? So, how can I replace 1 Newton meter moment in sys by using a force or a displacement value Example, suppose the superior end plate of C4 is approximately 25 millimeters from the center rotation. For the equivalent force is 40 newtons. So you could apply 40 newton anterior posterior at 25 millimeter offset, which generates exactly 1 Newton meter. Yeah. The problem is I don't have this offset. So what I will do here, could apply 40 Newton anterior posterior. So it will be slanted, yes? Because the moment in the paper is like this. So I can imitate it or replace it with the force, 40 Newton meter force. Slanted. Only a small problem is that it says anterior posterior. So the problem is that in this paper, it's posterior anterior. You see, this is posterior side. And this is anterior. The anterior of the spine is inside the body. This is the body side, and this is the outside, the back. So we say posterior to the back. The problem is it says 40 Newton anterior posterior, which is counter to what they say here. Because the direction is posterior anterior. Now, who is wrong? I will give a suggestion to ChatGPT and ask it. Maybe ChatGPT is wrong. Maybe. Can you say from the attached image if the force, the 40 Newton anterior force that you suggestion is I don't know how to say, correct, or the moment seems opposite to what you suggested. It looks like posterior anterior to me. The moment in the image correctly applied, the moment in the image. All right, let's paste. Copy and paste. Okay, it works. I worked very much with ChatGPT today. I don't know if I still have free questions. I don't want to create an image. No, please. Maybe it's giving a suggestion. We can only hope. Making the first draft. Oh my god. So no additional question. We're close to the second hour. Polishing details. Oh my god. So if you're questioning, hey, how does ChatGPT know about the C4 vertebrae? Is I have resumed what I asked today. So this is why it kind of remembered. Here, from my experience, here stops or never finishes. At this moment, one last week, it kind of stops. So what I will be doing is that I will apply an additional Newton in this direction, taking into account the fact that there is, as it said, an offset of 25 millimeters. The offset is the arm of the moment. Yeah, one last week and it stops. Let's Let's let it work, why not? I said something like, this is already slanted, I don't want to be slanted, because I think it's not slanted in the paper. No, it's not slanted. Let's make it perfectly vertical. And to make it perfectly vertical, the easiest way is to create a coordinate system in exactly this point, coordinate system, and I will rotate. I will rotate about the x axis. Rotate x, how much? 5. 10. Yeah, it's perfectly vertical. So now this force, which is force 1, will be applied according to our coordinate system. Why? Because I would like to have the slanted thing. Let's duplicate this and let's do something like -10. Look here. Yeah, it's slanted now. Let's do it -15, why not? Yeah, let's duplicate this, select the second coordinate system, and I promise to have -40. And somehow we kind of replaced the absence. We filled the absence of the moment. We kind of replace it as the AI advised, which is a good advice, I would say. So we kept the suggestions from the from live stream 12. All right. Do we have here 70 or 100? We have 100. Save. For fun, let's see how much the FEA takes for fun. Oh, it works. Only we need to clear generate data and resolve again and again, maybe. Do we have any questions? No. All right. I promised to rename it to stream 28. E1. Let's save. So the solving started. Let's see if it works. 1 hour. 1 hour is not so cute. What can we do? The mesh is pretty coarse already. $52 minutes. 52 minutes is nice, but it's not 20 minutes. So let's stop. And let's advise here some some time steps. One 8 minus 6. And let's see the difference. I don't think it will make much of a difference. Maybe in the end I will make here 0 point. Yeah, I will half. Maybe the end time. I will split it in half. Maybe. If the difference is not noticeable. If we still stay with the 50, above 50 minutes of solving. So how much does it take? $50. So no big difference. I can, however, make the mesh more coarse. Can I dare to make it more coarse? Let's not make it coarser. Instead, let's half the end time. So we should be approaching 25 minutes for solving. Maybe we'll not wait 25 minutes, but if we pass, I don't know, maybe the half of the simulation, if it looks nice, maybe we can stop the live stream. So let's let it cook. Where was I? Let's look at spine FEA, for example. Here we have something. Here is just a vertebrae. Come on. All right, and we do have simulation. Spine stimulator for pain. What? Who wants to stimulate pain? In principle, we want to get rid of the pain, not stimulate it. Yeah, no FEA. The FEA looks nice, but the mesh is awful. Spinologists. Do you have something more? Spinologists? It's because if I see correctly. No discs, by the way, no discs. Oh my God, what a work. Is this a true screw? I don't think it's a true screw. You cannot screw in. No, it's not possible. So maybe it's not a screw. The head is separated from the shaft, from the stift, let's say. The head is separated. Maybe this is why it can take this position. No discs, because the FEA is too complex after all. Oh my God, so much. I mean, in reality, there is so much work. Oh my God, just imagine from this to this. So much work and pain on the patient and effort from the doctor, from the physician. Yeah, nice work. Could have been finer. I mean, the mesh could be finer. Nice work. So from 25 minutes, we have 26. We're on the right track. I think the time is going in reverse. Oh, there is a small problem here. So from this cartilage on, nothing happens. Let's check a little the impact. No, it's correct. I do have contact between the here and here. So, applying force, I think it's not enough in this case, or at least in this scenario with my conditions. I'm contemplating about having to apply a displacement, maybe, instead of force. The problem is the cartilage is so elastic, it gets squeezed and it doesn't propagate the force. There is this solution. Either I make harder, stiffer cartilage, yeah, this is the only solution, to make a stiffer cartilage. What properties do we have here? I have 10 megapascals for young models. This is much. Look here, didn't finish. Can you estimate Young's modulus for the disc vertebrae? I will say I will help it. Estimate. Come on. Yes, of course, but it's, you know what, let's go with higher. I need the cartilage to be very stiff, let's say. I have 10, I can go to 25, let's say. Oh, good things happen to those who wait. Yeah, let's look a little on the stress, just saying. Now I see that I didn't apply the plate optimally. The plate should have been shorter, and the plate should only enclose this portion. This, look here. Here. Yeah. In my model, the plate doesn't do much because it allows flexibility here. The plate should be focused only here. Yeah, it's a mistake. But you know, it doesn't mean that we need to perfectly copy the paper. Only it's not much use, let's say. What I can do is move this here and run with both cages. This would solve. all the things. So let me open space claim and do what I said. I will copy the cage and put it upwards in order to compress both cages with this big plate, if I want to have a big plate, because in the paper they used a smaller plate only for one cage. So I was here. I should again yes, doc. Do I stop it or not? Let's stop it, even though it looks very nice. But let's make a logical and useful model. And it's another case, you know. We don't need to copy in the utmost detail. We can be creative. Let's animate a little. It's not so. Let's assign auto scale. Oh. Yeah, this is a little better. Let's make the cartilages stiffer with 24 megapascals. Young's models. Super, we're on the very good track. Let's go here and delete the original simulation, duplicate this one. Let's close space claim. I don't want to work externally in another space claim session, because this will mean that I need to reapply some boundary conditions, let's say, upon the import of geometry. So I will edit this geometry in order to have to keep the most of the boundary conditions, most of them. This is called, it's a copy, I don't need to rename it. Double click. So yes, we'll be more creative. I mean, we'll have two cages because we have a bigger plate. Perfect. Delete here. And let's kind of move it. Let's make these transparent and see how we can move. Is this correct or not? It looks very nice. Let's see it in section view. Yes, we're rotating here, and it's nice. Let's keep only these three parts, hide others, and we're running the interference command. All right, now right click, save. When saving the entire project, it saves also the 3D model. And let's go for interference. It should be, we should have no interference. In the meantime, I said that for the cartilage, I will make it 24, I said. Should we be so desperate? And plate intervertebral disc, let's make it 24, and yeah. What Poisson ratio do we have? 4. Let's make it 4, yeah. It will be pretty stiff, let's say. 0.4. Stiffer discs. Slightly, in order not to panic some people. So while the interference command is running, let's see if we have any other question. Wow, another tutorial. I'm in. Yes. When you have the time, because now it's 0 audience. So you're in the future. Thank you for the appreciation. Hopefully this video will be available for watching later. It's past midnight here. We'll come back to it soon. Yes. No problem. Yes. Go to sleep, it will stay. It will stay, no problem. Also in my country here, it's almost midnight, so yeah, in other countries. In Asia, maybe it's morning now, so I understand. Come on, why did I run this command when I knew there is no additional interference? Oh, another alarm. Please forgive me a few seconds. All right. Let me write down. Come on. So, where was I? Biomechanics. Oh my god. This looks promising. So there are no interfering bodies, all right? Save. And let's also save it externally. Source internalize all. All right. Double click. I keep space claim in order for the geometry to be updated faster. Now it will make more sense. It will make all the sense in the world having two cages. It's not possible to fixate, to restrain something having a flexible element. Yeah, this disk was in the way and it made no sense. This is why a smaller plate was used for one cage. We have a larger plate, then we're going to use two cages. At this percentage, I have seen that it takes more time. When having body interactions instead of contacts, everything is kind of kept as needed, while having contacts upon refreshing the geometry, it's heavily modifying the contacts, let's say. So it will be better with the body interaction. Come on. Why do you keep closing this window? Why? Update. Update. Yes. This is what we wanted. This is what we needed. Save here. Um, let's see if the mesh works. Now the cartilage is a little, it's much stiffer, let's say, more than double. Oh, don't tell me we will have this problem again and again. Oh. You know what? Let's close this. All right. So, do we have a mesh? Yes, we're blessed. So we need to delete all the contacts, and for this specific body interaction, this one, for this one we need to include the cage, this cage. And for the next body interaction, we also need to include the cage. And this is it. Let's switch the units to millimeters. And so on, yes. Forces, is it applied correctly? Yes. Force, yes. Fixed support, yes. The load is not too high. So we will have values, but we will not have big displacement, let's say, yes? We'll have stresses and so on, but we will not have very spectacular displacements or whatever. Save, so. Yes, we should be fine, I think. The load of 7 kilograms and 4 kilograms, 76 newtons, and 40 newtons come from the, let's say, from the weight of the head, let's say. This is why normally we should not increase these loads. Normally. Yes, it started. Let's see if we still have 25 minutes. Oh, even better, a little better. Where was I? Any question from the live stream? No, let's go for biomechanics. I don't know, can I? I wanted to cancel these results to not be shown. How do I cancel one? Don't recommend this channel. This is what I wanted to say. It's not possible to publish such ugly FEA. It's not possible. Look here. What is this? What is this? This is the patella, yes? Why? Why? It's so sad and comical at the same time. Oh, so much AI here. In this thumbnail. Let's see what we have. Bacchus fan, okay. Maybe this person is. The graphic is very nice for this thumbnail. No like? I think I will give a like in a few seconds. Yeah, it deserves that. Well, what is the of cortical bone? Come on, orthogonal cutting of cortical bone. Arrowhead impact. So what began as a bullet now is an arrowhead. Ballistic impact is of Kevlar. What is this? Something is wrong here. Where is the soccer ball? Where is the soccer ball? So this person made some FEA and included the word bone and lots of things. It kind of switched, let's say, the existing simulations, and it included the word biomechanics and bone in order to create a package or something. Yeah, no problem. Kudos. Let's also, I said I will give a like. Let's also show a simulation with a ball, yes? It's pretty old, this simulation, this one, right? This is a ball, yes? It's empty on the inside. I think there is air defined. Yes, it is air defined. So this is coupled Eulerian-Lagrangian simulation. I think. So nice. It's coupled Eulerian-Lagrangian. So nice. I will not comment too much. So this person is kind of repurposing all the FEA and is giving it a biomechanics flavor, let's say, but it's little too stretched. Where was I? I was here. We do have 20%. Let's see if it works as we hoped. Oh, yes. Oh my god, spamming. It's not a problem if you spam with good work, but with such bad work, oh my god. So it kept the femur fixed and rotated the hip. It's kind of laughable. Not impossible, but laughable because the femur should rotate, should move in principle. Yeah, nothing interesting to see. So let's review my other spine simulations. This is very nice. So this vertebrae is cut. And we can observe the assembly with pedicle screws and wires, the rods, and without. This is without, this is with. And we can see the effect on the cut vertebra. Is this possible to occur? Hardly possible. Because of course, this is why we have discs to break from the discs, not from the vertebra, of course. But let's assume a bad person with a grinder, an angular grinder with a chainsaw, let's assume it cut the vertebra. Why not? We can assume. It's a nice work. It's not my best work, but it's nice. It was very complex to make the 3D model meshable. It was very complex. Lots of work. Here is kind of breaking. The disc is too soft. And I didn't assign like a pinball radius to cover most of the disc. So it's only touching in a small portion. This is why it kind of flies away from here. So yeah, I will do better next time. Look here, yeah, so it's the contacts, yeah, between this disc and the surrounding the mating vertebrae. These contacts, these interactions are not very cute, very correct, let's say, very decent. No, it's a barely made contact. The problem was I was working with the 3D models done with the meshing. I had so many errors that at a certain point I said, you know what, I will just stop and accept the results because it was so much work. It's the first time when I see an FEA with spine and skull and leg Yeah. There is no brain inside here, and the teeth are not separate. I have other simulation with brain, but until now, because I didn't find a brain with meninges, I found one, but there are some interferences, and it's very hard to resolve, to remove those collisions, because it's a topological problem. It's a problem with any software, for example, a space claim, to understand what do you mean, what is difference between inside and outside. So just imagine that the brain is surrounded by three meninges. Yes, pia, arachnoid, and dura. Yes. The problem is I found something. Yeah. So the brain is so convoluted. It's very hard to find a model of meninges to cover all the striations, let's say. But I found a 3D model, only it has lots of collisions. So pia mater, the one that touches the brain, collides interferences with the striations, let's say, from the brain. Then the dura mater doesn't perfectly touch the inner skull. So why I'm telling you this? Because I would like you to see the problems with the brains. Look here, not having those meninges at all. This is what gives us. According to me, this simulation is awful. According to me. So imagine that we need to envelop the brain 3 times. If I were to make some wrapping, the problem is the facets. And I need to make 3 wrappings because we have 3 meninges. And the last, the most external meninge, the other, how it's called, dura, the last one, yeah? The dura mater needs to take also the shape of the skull, of the inner skull. It's so complex. This problem is in my background, is pending, I would say it's a work in progress, even though it's at an intellectual level. I am only thinking about this, how to approach this. Yeah. The meninges have many roles, and in this case and in our simulations, usually regarding and treating the structural side, we ignore here, because we don't have the meninges modeled, we ignore here the support role of the meninges support and kind of fixate or restrain, let's say, the brain. And yeah, not having the meninges here, the brain dissolves. The same case here. Here we also have the brain. Look here, yes? We do not have meninges. For a beginner, or maybe for a medium person, maybe they will say, yes, cute, but not for me. So I'm not getting fooled by this simulation. it will be better in the future. It will be better. I will improve. Set audio to 0 audience. So it looks so nice. Do we have a touching here? Yes, I think we have a touching. Huh? Maybe. No, but I don't understand why. Why there is this maximum here? Normally the stress should be scoped. We should differentiate softer bodies against harder bodies. Look what I was talking about. So let's select softer bodies. This is soft. This is soft. This is soft. And harder bodies, let's also include these ones, the bones. Now let's deal with the harder bodies. And now the plots will make sense. Right-click, switch to automatic mode. So look here, the plots for the softer bodies, softer compared to the titanium. Yeah, they are clearly touching here. All right, and this is the plot, the stress plot for the metallic bodies, for the titanium parts. Yeah, it looks so nice. I like the values. The values are small as on the paper. Even though it's not still finished, but we have 70, yeah, 3/4 simulation. But the values are very nice. It looks so nice. Oh my god, it looks so nice. So let's wait 7 more minutes. So I said about brain. For fun, let's look a little in my repository of biomechanical models. And let's hit a search with no. Let's at least see our what brain parts do we, what brain geometries do we have? Complete brain. It also has the cerebellum and the stem, the brain stem. What is this? I will look a little at the brain model, then I'll look at the child brain. I would like to take a look why did I assign so many exclamation marks. Yes, just imagine 658 geometry models only in biomechanics. Yeah. It's this is the problem with making envelopes or wrapping. Yes, so we have the shrink wrap command. This is the problem when you have small details. For example, how do you shrink wrap here? How do you fit? How do you fit a surface here? And imagine having three Meninges, and you need. Normally, it should envelop only in this manner. Yeah. Of course, we do not have a meninge here inside. It should envelop like this. And the easiest way is to envelop it with such commands, shrink wrap. And the shrink wrap covers the entire geometry, not something specific, let's say. So I said something about because I'd like for you to see the brain with the Meninges that I have. That it's available for free. It's not my work, let's say. So how was I treating this? Look here. We go in visual environment. This is a K file specific to LS-DYNA, yes? Head brain. Like you can... head brain and head skull. Do you wish to know? Yeah, I think this is what I was telling you. It has the Meninges. I am not an expert in this software, but I am using it to file export. So imagine I imported the K file, an LS-DYNA mesh, and now I would like to export it as STL. IGS usually generates surface bodies. Let's go to STL, and we have desktop export. I was thinking about also opening other part, but we don't need. So let's open this. I exported an STL. Look here. This is what I have closest to the Meninges. Yeah. In order for, look here, the dura mater, the pia mater, and there should be also the arachnoid. Which I do not see it. Maybe it's this one. Maybe they rename it. And so, for example, can I hide this? It's only this cap. All right. So, for example, let's make something resembling a section view. Double click, and we're going to make through the kind of a middle, we're going to make a section view. Let's suppose this is the middle. Look here, yes. So we do have two Meninges. We should have three. This is just a cap. It's not useful. Let's go with the plane more towards the brain, and because we cannot see in the gap here, we cannot see many things. Yeah. Main head brain. But what is, there was another file, if you remember, and the file was head skull. I'm curious, what is head skull? And maybe that goes here. Let's see. Maybe the previous file goes here. Let's export it as STL on desktop. Main head skull export. All right. So our FEA successfully finished. I'll delay the results, seeing the results a few minutes, in order to assess if we have a decent brain or Meninges. Oh yes. Now let's go in the again in the section mode. So clearly this is the skull, and here this is the cerebellum. Here, I don't know what to say. Pia mater and foxillary tentorium cerebellum. Subarachnoid. Let's hide this. For cerebellum, I don't care. Cerebellum. This is cerebellum. What the actual? Cerebral cortex, I don't care. Internal cable. So this is, I think this is what we call brain. Then this is a layer, this is a layer, and this is a layer. Maybe. Yes, so for example, you can see here, this is a layer. You can see here, this is a layer, and this is another layer. Personally, I do not see three Meninges. I see only two. But you know, 2 is better than 0, so yeah. Now I remember. If you're not familiar with these models from Toombs and from Piper, they present the solid parts. These are solid parts. When you see a full cube, look here how the cubes look like. These cubes are full, they have all the sides. And when the cube is broken, this is an unfolded, an envelope of the cube. Then this means these are surfaces, let's say, faces. So for example, let's hide everything that is surface and let's keep only, for example, the skull has the solid part of the skull. Let's say skull is a solid body, even though this is STL that is not solid. But this can be easily exported or solidified, let's say. And this is a surface. And you know, we usually in explicit dynamics, when we're dealing with high velocity impacts and something similar, we need to have and to work with only with surface bodies usually to save computational time. Look here, once I have hidden the open parts, the surface bodies, they begin to make sense, yes? So we have a solid here, solid here, solid here, solid here. Only one problem is that we're kind of missing a meninge, let's say. Yeah, there is too much gap here. Yeah, so I will reevaluate, remake the judgment on this, because yeah, it's worth it. It's a problem that stays on my brain since a while ago. So the brain here, you see how smooth it is. It doesn't have the usual striations. I don't know how they're called in English. Circumvolution, okay. Circumvolutions. This is why they succeeded in making these meninges. Yeah, they enveloped the brain because it does not have the usual circumvolutions, the usual striations. Look here. All right, at least, here it's the only interference. There are some gaps, but we do not have lots of interference. Only small interferences. Let me save this because this is very important to me, at least. Where was I? Checking to see if there is. All right, we'll come back to some. Yes, do that after you get up. Let's see the results. There is a scaling here, 15. I can show it to you through scale, and it's not so evident what happens. Let's move it to 5. 5 will be better. Not exaggerated, not inexistent. Largest strain in the hyperelastic bodies. It's expected, of course. Strain, and the strain should be, separated, discerned. We should discern between evaluating the stress in hard, in stiff parts, and evaluating the stress in the softer parts. Let's remind you, the stress in these parts. Lower values is expected for softer parts. It looks even nicer with this. Yeah, it's so nice. Force reaction. We have a decent value. Not this one. This is not so decent. Because you applied 70 plus 40, 100, almost 110 or something, 115, and we have, this is not so cute. We do have a shock, when you apply this load, instead of having a real time, this load should have been applied in maybe 1 second or more. Maybe, When you have such a shock, then such a force reaction is expected, yes, due to high acceleration. It's like an impact simulation, like a shock simulation. Energy, and remember not to despair, we do have this compressor, yes. And if you want to evaluate the pressure in contacts, you know what I would do? I would do something like this, duplicate without results, and I would select, let's say only these ones. This is one thing. And the second thing, for example, you want to see the pressure in the discs. Just select certain, unfortunately we cannot discretize. I wanted to select this face only, but it's too big, too united, too joined with the other faces. So let me show you the pressure, for example, in these faces, not solid, that's faces. So a maximum of 0.16, but other values 0.1, let's say we have something big here, 0.12. I'm curious what did the paper say, if they have pressure. Do they have pressure for Mrs.? I'm curious if they have contact pressure. No, I don't see so. Nevertheless, we do have a different scenarios because we have two disks. What is this? And they made a table with the values. Yeah, perfect. So for you who didn't know how to acquire the pressure on some faces, this is how you do it in Explicit Linux. Ladies and gentlemen, this is all from my side. Thank you for your attention, and good luck in your simulation work, in your simulation life. See you next time. Bye-bye.